All right, so we're going to just do example 3 and example 4, and this is probably going to be it for today. So example 3, put it in your notes. And this one is going to be to describe the dilation and reflection in the function. Okay, and then we're also going to graph it. So then graph. So the function that we're going to look at is g of x equals a negative 2/5 x. Okay, so if you look at this function, you can see it's a linear function. So let's just establish what the parent function would be. So the parent function would be, let's say, f of x equals just 1x, right? So when we look at these characteristics, the first thing that I'm going to notice is that we are multiplying right there. We have a negative value that we're multiplying this function by. So since we're multiplying by this negative, we're going to have a reflection. And the question is, is it a y-axis reflection or x-axis reflection? In this case, you could consider it both. One way you can, and we don't have to put both of them in there. We could think of this as, if we rewrote g of x, we could say g of x equals negative 2/5, right? And since our parent function is x, and this is x over here, we could think of that being a substitution, and we can just write this as f of x, right? So we're really just taking negative 2/5 times f of x. So if we think back to what this is going to be, right? We have an a value. My a value, or my multiplier here, is negative 2/5. So because it's negative, right? If we go back to, let's go back to those a values. We're kind of looking at this one right here. We're multiplying the function. We're multiplying the function by a value, an a value, that is in between 0 and 1, right? The absolute value of negative 2/5 is 2/5. And so this is going to be a graph that is compressed vertically, or this is one way we can think of it, right? So my a value is negative 2/5. What that means is that number one, the graph will be compressed vertically. Right? The graph will be compressed vertically. Also, because we have a negative value out here, right? We got a negative, so it's really a negative value times the f of x. If you think back to our rules over here, we can think of this as a reflection in the x-axis right here, right? It's just flipped over. So we can say graph will be a reflection in the x-axis. Okay, so if we're following those rules and we talk about the dilations that can happen, these two things I would put, right? We're going to have a graph that's compressed vertically because the a value is negative 2/5. Right? And then since the a value is negative, we can think of a reflection in the x-axis because we're going to follow this rule that we have here. So if we were to show that, and we won't actually sketch this graph out, we'll just show the result of it here. because there's a lot of easy ways you can think about this. You can also just think of it, hey, look, it's a line, and instead of a slope of 1, it's a slope of -2/5. That's how most of you would probably think about this. But we're trying to generalize the observations of these transformations that we're looking at. Okay, so there's the parent function. And so what did we do here? Well, if we took f of x and we made it -x, you can see it's a reflection over the x-axis. Let me say this is G. Change the color here. Maybe I can't. Yes, I can. Right? So when we make it -x, it is a reflection over the x-axis. We can think about it as. You might also be saying, well, isn't it also a reflection over the y? And yes, it is. There's actually both that happen here. They're equivalent. So either one that you would put would be correct. And if you put both, that would be great, right? Because both of them are true. Now, if we make our a value 2/5, right? So there's 2/5. We could think of this as being a compression. And now I'm going to take the negative out of it, right? So we can think of this as a vertical compression. So it's up here, but then if we compress it vertically, it gets closer to the x-axis, and we kind of squash it down closer to the x-axis because its a value is 2/5, right? So that's how it looks. Now you also could look at this and say, doesn't this look like a horizontal stretch? It looks like, if I think about a horizontal movement, I'm sort of stretching this out horizontally. And that is true, right? You could think of either transformation you could think of, and all I need you to do is in this case, give me one of them. So if we look at those, these two things would be great. The graph will be compressed vertically, and the graph will be a reflection in the x-axis. But if we really analyze it, it's also the y-axis too. All right, so we're going to do just one more example like that. Let's look at, let's say, example 4 here. And we're going to look at function right from our book. And let's say that g of x equals a -2.5 x, and this is all squared. So now we have a quadratic function here. And again, we're going to describe the dilation and the reflection here. So let's think about the parent function, right? The parent function, f of x, would just be a x squared, right? So when we think about what this is going to be, is this going to be a, a vertical or horizontal stretch, right? We can't really just substitute in here, right, an x squared. What this is going to be is if we plugged in -2.5 x into this function. So we can think of g of x as really, in comparison to f of x, as f of, instead of x squared here, we have -2.5x. So -2.5 x, just like that. We could think of it as like that composition right there. So really, if we break that down, then we can think of this as f of like -1, that negative is going to be there, and then times some a value and times some x value. Right, so if we kind of look up our charts here, what kind of dilation do we have? Right, this is 2.5. Our a value is, we can think of it as being 2.5. You can also think of it as being just -2.5, whatever the case is. If you go back to our chart here, this is going to look more like this one right here, okay? Because we have an f of something times x, and our a value is greater than 1. It's 2.5. So we can think of this as a horizontal compression. We're going to think of this as a horizontal compression. And so we go back there. Number one, we're going to say g of x is a horizontal compression. right? It's a horizontal compression because of looking at what we have in this function right here. We have g of x is negative 2.5x all squared. So our a value is 2.5 or negative 2.5. It's inside of that squared term, inside the parentheses. So we can kind of think of it as a horizontal compression. And then what else? If we look at our reflections, right? In this case, we can think of this one as a reflection in the y-axis because we have f of a negative x value here. Instead of negative f of x, we have f of negative x. So number 2 in this function, if we go back to our rules, we can say g of x is a reflection in the y-axis there. It's going to be a y-axis reflection. So really, nothing's going to change, right? It's just going to reflect over the y, and those y values aren't really going to be reflected and go negative. So this is what I would put for that second one, right? So we sort of have to analyze what these functions are. Think about the a values. Think about which dilation, which reflection, which translation this is referring back to, and describe the changes. Now let's take a quick look back at Desmos. So here's my x squared, and let's look at our new function, which is parentheses negative 2.5x end parentheses, and this is squared. So you can think of it, right? It didn't go negative, right? So it's not an x-axis reflection, it's a y-axis reflection. And if we do this in parts, I can get rid of the 2.5. So we can look like that, right? So we can say, look, this reflects over the y-axis because it's negative inside the parentheses. Okay, so it looks like the same thing. But if we add an a value of 2.5, right, we can think of this as a horizontal compression. So the graph is being squeezed closer to the y-axis. Okay, so horizontal compression. And again, you could look at this problem and say, doesn't it look vertically stretched as well? Yes, there is an equivalent vertical stretch, but in this case, we're only focused on the horizontal compression because of the way that we wrote this function. Okay, so that's it for example 4. You can get on part 1 of your homework, which is in Canvas, and when I get back tomorrow, we will finish up 1.7 and do more review and answer questions.